What were those fundamental entities from which the stars and galaxies have been built? Physicists are trying to answer that question by taking matter apart, looking at the pieces. In effect, looking back in time at the earliest stages of creation.
And at these earliest stages of creation, matter existed in a weird and wonderful primeval form.
I suspect that at the very beginning of the Big Bang, nature was quite simple, and it was only then, as the incredible temperature began to cool off, that all the rich variety of forces and particles that we know about today began to appear. When the universe was so extremely hot, a curious state of affairs prevailed. Let's see what our calculations tell us. Right at the start of the Big Bang, there was a high degree of symmetry among all the different kinds of force and all the different types of particles that filled the universe. But that state of affairs lasted for only an instant. Almost immediately, the perfect symmetry was lost. This all happened in perhaps 1/10,000th of a second after the beginning of the Big Bang. At very small scales, matter now is much like it was at the beginning of the Big Bang. There's a high degree of symmetry among all the kinds of forces and all the types of particles. We've just arrived too late in the history of the universe to see this symmetry easily, so we have to try to recreate it in our laboratory, making little bangs in our accelerators.
The protons are in the machine. We're ready at this end.
In short, particle accelerators, it was hoped, would provide mini Big Bangs, tiny examples of the original conditions under which all matter, even dark matter, was formed.
I call it sometimes the greatest adventure of the human mind, which is the discovery to penetrate as far as possible, to understand as much as possible about his universe, what he's made out of, and what matter is made out of, that this is just like a great exploration.
It was an exploration that required particle accelerators able to generate energies close to those that must have been present at the Big Bang.
So, Hans, looks like you finally got collisions.
And this meant building giant machines.
It almost seems a paradox that the smaller the thing you're looking for, the bigger the instrument you need. Near Geneva, the mysteries of the atom are probed in this gigantic laboratory. It straddles the Swiss-French border. This one, sited near San Francisco, is 2 miles long. Even for an experimenter driving a fast car, it's a long ride. Yet the electrons that fly along the accelerator do the journey in 100,000th of a second. The machine tortures matter. Picture by picture, we catch glimpses of how the universe looked a few minutes after the creation. The particles produced in these collisions are much too small to be seen. Their presence is revealed only by the tracks they leave behind them as they pass through the detecting equipment.
The way we do find out about this proton, the first kind of experiments that we've been making, is to tear the electron off the atom and accelerate the proton faster and faster and let it plow into a mass of atoms, into ordinary matter, hoping it'll hit one of the other protons in a, say, hydrogen gas. And then see what happens, what comes out. It would be like trying to find out what a watch is made out of and how the mechanism works, by the expedient of smashing 2 watches together and seeing what kinds of gear wheels fly out.
These patterns, the lengths and shapes of these tracks, describe the life histories of particles. Some of them live only a few billionths of a second, and the tracks are the only evidence of their fleeting existence. Interpreting these pictures, deciding what they tell us about the universe, needs colossal imagination, the finest scientific minds of our time.
What's interesting is that these properties of atoms that we found here are the same, we have found out, as the properties of atoms on the stars. It's the same atoms. It's a universe that we're looking at. So we're not just exploring a little thing. And maybe you go very deep and it looks smaller and smaller. It's only small in dimension. As far as the universe is concerned, it's all-encompassing. It's universal. So it's a tremendous adventure. It's apparently important. It's the result of curiosity. It's impossible to stop.
Back at CERN in Geneva, the particle experiments soon attracted the curiosity of the local population.
Alors, on chasse les atomes là, avec la vitesse de la lumière,
Ouais.
300 000 km à la seconde,
Ouais.
contre là, et puis par le touchement, eh ben, ils éclatent.
Ouais. Et ça vous intéresse comme physique, vous?
Ah, bien sûr, parce que pour moi, ça c'est l'avenir là.
As many documentary filmmakers have come to realize over the years, particle physics has a habit of becoming insanely complicated very quickly.
What do you think exactly of renormalizability behavior or instant variance? Isn't it, as you go along the s-axis, a series of delta functions?
CERN is a strange and baffling place. Its essential events are invisible. They take place inside stainless steel tubes or inside physicists' heads. The physicists' work and ideas are as difficult to understand for us as the building bricks of matter are for the physicist. Like them, we must rely on echoes and shadows like these. John Cherub visited CERN again for the purpose of this film. He talks with John Bell, a CERN theoretician, about